it's a different microphone. You changed microphones. But no, it's angled. It's got a fixed angle. Yeah, the other one has a little thing that rotates. It's fine. It's fine. I can live with it. Okay, so this is the finger. How do I prove this? What's the proof of this? So we want to map left to right, and I want to map right to left. What's the left to right's real easy. What do I do to get a map left to right? Adrian? I'm not going to move till you tell me the answer. Yeah, okay. I'm not going to give you any body language clues. It's sort of like I can go like this or like this.
Catching me on the fly. All right.
Yeah, on the fly, right? So let's start with something here. I have something. Yeah, I have something here. So I have F. So we'll just start your brain sort of. We're starting off in first gear. So okay. So here's a G map. How can I get a map? So now I want a map from V to U. How do I get a map from V to U? To make the obvious guess, how can I get a map? So what I have is a map from here to here. And what I want is a map from here to here. It doesn't have to be an H map. It doesn't make any sense, in fact. So just a map from here. How do I do it?
What do you mean it doesn't have to be an H map?
No, it doesn't have to be a G. It doesn't. It's an H map. It has to be an H map. Yeah. Okay. But just forget about H for the moment. Just how do I get a map? If I'm given a map from here to here, how do I get a map from here to here? Hello? Evaluate at 1. That's exactly right. So in other words, there's a map from here. No. Yeah. So I compose it. So what I have is I have a map which I call omega 1 from end U to U, namely, I just take F goes to F of 1. And now, if I look at RH of F, so this is equal to RH of F of 1, and that's equal to F of H, and that's equal to sigma H F of 1 by the definition of induced, and that's equal to sigma H lambda F. Okay. 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 So that's a map that goes this way. Okay, how do I get a map going back the other way? So this gives left to right. So composition. So the way to say this is, so what I have is I have a map omega 1. I better keep putting the 1 in there because that's important. From end U. So the way to think of it is I have an H map from this, and lambda 1 RH of F is equal to R sigma H lambda 1 of F. Okay, and then I compose. So given F from V to end U, I just compose with lambda. So the map from Hom V end U goes to Hom H VU. F goes to lambda 1 composed with F. Okay. Okay, so that's easy. So this is a map from left to right. How about from right to left? I don't think any of us have actually told you this part. Shame on us. So let's see. So I'm given phi from V to U an H map. So what we have is that phi pi H V equals sigma H phi of V. Okay, since we have it written, I'll write it out thing. So we have this map, and we want to get this map. So we want to get a map from here into here. So for each V, so suppose V is a member of capital V, and we want a function in the induced space which I'll call f sub V in the induced space. And the way to get that is I define f of V of G to be equal to phi of pi of G V. And then I can check f of V Hg equals phi of pi of H GV equals phi of pi H pi GV equals sigma H phi of pi GV equals sigma H FV, FV of G. Okay. So like in any little Mozart piece, this is the theme. Okay. So now we're going to do variations. So I really should write this. Let's call this Variations on a Theme of Frobenius. Actually, I've never read Frobenius. No, nobody in this room has probably ever read anything by Frobenius, and certainly, and not me. I should go check it out. Okay, so this is all fine. It's golden. It works very well. You can check. It's for you to check that this is actually the inverse, but that's completely clear. No questions so far. Okay. Okay. Now, suppose, let's look at the case we're interested in, which is SL2. So now take, and this works actually pretty well. So everything that I've done works well as long as this is finite dimensional and this is compact. Then I just have a few worries about continuity, but they're all rather easy to check. So, huh?
Finite co-dimension and that is compact.
No, if this is finite dimension, and this group is compact, and this is closed, then everything works all right. There's some continuity questions to be, but otherwise it works fine. There's still no serious problem. So, I assume the representation is continuous. Okay, so that's an easy variation which I won't even bother with. Okay, so now let's look at SL2. And H equals P equals AN. Okay. And I want to let sigma U equals a finite dimensional continuous representation of P. Okay, now, yeah, okay, we'll just do that. So let me make a few remarks. So there are things we're just sort of leaving up in the air, and I want to tie down some more loose ends. So the finite dimensional representation of P is equal to, it's equivalent to a finite dimensional representation of the Lie algebra of P plus the maximal compact K intersect P. So that's a very trivial case of things that we've talked about. So we've constantly harassed you with this theme that the representations of the group are not the same as representations of the Lie algebra, but this is finite dimensional. And so in this case, and everything we works through for an arbitrary group, really. And so it doesn't have to be a reductive group or anything. So finite dimensional continuous representations of the group are equivalent to this. And the reason for throwing in the K is to handle the what? What's the purpose of throwing in K as well as the Lie algebra? Yeah, I have to deal with connected components and pi 1, pi 0 and pi 1. So that's the reason for throwing in this. Okay, so I need both of those. But you can travel back and forth without any trouble. So the representation of the Lie algebra takes care of what happens on the connected component, and this part takes care of what happens on the other component. It also deals with possible covering problems. Okay. Okay, so I have this. And now in this case, there are several. I'm not going to write ind all over it. Well, I will actually. So, no, I won't. I'm not going to write ind. So I'm just going to write I. So I of sigma from P to G equals something. And now, but now I'm leaving things up in the air because actually there are several different things. So the first thing is, the first induced representation is C infinity of G with values in P such that f of PG. And now, for reasons which have caused trouble, I have to throw in the delta 1, or I do throw in the delta 1/2. Okay. And then I also have contained in this, I have the k finites. So this is the k finite vectors. So this is the right k finite vectors in this space. Okay, so that's what the bottom one is. So there's no superscript there. In between, there's some other representation. What's another natural space in which to act? Somewhere in between k finite, and the trouble with the bottom one is, of course, that the Lie algebra acts, so this is a G space, and there are various topological considerations, but the quotient of G quotient P is compact, and so the topological vector space problems aren't very deep. This is a GK space, but not a Lie. Actually, but what lies in between? What's another space that lies in between? Just to sort of give you some perspective.
Analytic.
Analytic, exactly, real analytic. And so we'll call that this. So I just put so these are all three different spaces. This is k finites, this is analytic. So the group X on this is a rather small space. What's true is that this is actually the smallest G space. It's not an easy theorem to see as far as I know, but it turns out that this is actually the smallest space in which G acts, which contains this.
The whole thing is a G space.
Well, this.
C infinity, the first one is also a G.
Yeah, they're all G spaces, but this is the smallest one.
Oh.
Absolutely the smallest one. So it's not an easy theorem as far as I know. Maybe Trappa knows better.
The smallest one which contains the k finite vectors.
Yeah, which has the property that its k finite vectors are this. So I omega turns out to be, we're not going to prove this at all. It's one thing, I tell you, the more we lecture to you, the more I realize we can't possibly, it seems like SL2 is a very small group, but there's just infinite things we're not going to tell you about. Anyway, this turns out to be the smallest possible G representation in a really strong sense. But as I say, I'm just trying to give some overall perspective with I as the associated k finite subspace. Okay, and yeah.
You mean I omega is algebraically generated by I as a G space algebraically?
No, it's
Because the space that I generates algebraically.
yeah. The answer to that is I have to say I was thinking about it as I was writing it down. It's something. It's the smallest one in. What's true is it's the smallest one in which CC infinity acts. So we've been talking about the group algebra. So the actual technical condition is it's the smallest one in which I can actually let the group algebra CC infinity
So now
act.
it is algebraically generated.
It's not, so it's algebraically generated by this. So there's some, okay. So I'm not going to, but you certainly, so again, I mean, I'm sure, I mean, you can just take some G space acting trivially, so that's not quite right, but you really want the group, we've shown many times over that you really want the group algebra to act as well, and the smallest group algebra you want to act as this one. And one reason we've dealt with CC infinity all along is we know that there are spaces in which only CC infinity acts in some sense, and this is the right one. Okay. Okay. Yeah. I can't yell. You have to yell, cause. Yeah, I omega, which is the real analytic functions here. So I just replaced this by analytic. It turns out to be the smallest possible G representation. That's REP apostrophe N with I as associated K finite subspace. But what I mean by smallest possible, I mean it's the smallest possible on which the CC infinity actually acts. Okay. Yeah. Huh?
Which group P do you take? A and
The whole upper triangular. The whole upper triangular.
M is contained in A in his notation.
I have never referred to M. The reason I never refer to M is because for the p-adics it doesn't make any sense. So I'm a number theorist, and every time I work with representations of real groups, I'm sort of thinking, well, we want to do automorphic forms, and if you want to do automorphic forms, the p-adic groups are equally interesting. Well, not quite so interesting as the real groups, and so you really shouldn't. You want notation that works for all things, and that's the only way to deal with that is to forget all these guys who write down M specially. So all this notation works perfectly good for p-adic groups. Okay, but the analysis for p-adic groups is trivial. Anyway, so I have this, and I infinity is something else. So there's some way to characterize I infinity which I won't say. I infinity is in some sense the largest interesting smooth representation, but I won't say more about that. There's some way to characterize I infinity as well. Okay. Okay, now, so also for this situation, I want to say that there's a Frobenius reciprocity. So we have different versions of Frobenius reciprocity. Okay, so let's write down the simplest one. And already there's a technical problem. So suppose that V, well, pi V equals the GK module. Okay. And then it's still true that, well, let's say a Harish-Chandra module. So it's still true that Hom GK from V into I U is equal to Hom P K intersect P from V to U. So that's a true theorem. And it's easy to see how to go from here to here, namely from left to right. Composed with lambda 1. Okay. Okay? But how do I go from right to left? So given phi, V goes to U. Oh, there's something else I have to say about, okay, I'll mention it in just a minute. Let's not worry about that quite at the moment. Given phi, yeah, how to get F, capital F, V to I, U. Okay. So look at your notes for what I do to the finite case and tell me the formula I'm going to write down. Hmm? Oh, it's on this board. Oh, right, it's on this board. So it's the same formula. So that's what we want to do. So what we want to do is V corresponds to FV, and FV of G is equal to phi of pi G V. What's wrong with that? Yeah, the group doesn't act on V. Whoops. So we put in a whoops. Okay. So the reason, in a sense, I think the reason we haven't written down this formula before is because we didn't want to face reality here. Okay, how do I get around this? Somebody besides you. I'll give you a chance to redeem yourself.
Sorry, I actually had a question.
Yeah. Yeah, no, it's fine.
Could you remind the definition of C infinity GU?
Yeah, it's just smooth functions from GDU. Use a finite dimensional space. Use a finite dimensional space, so there's no technical problems with this, because I just look at all, you know, you basically use Rn, so I just have an array of smooth functions. Okay. So how can I get around this technical problem? How do I define the map? So in the face of it, the definition doesn't work, but hello? Nobody has any bright ideas? You have a bright idea? Yeah, go ahead. What's your bright idea?
To extend it first to K.
Yeah, so what I can do is, there's several ways to deal with this. But the first way is, I know that G is equal to PK, right? And so I can write an element G is equal to P times K, and K acts on the representation. And I know what it's supposed to look like on this. So FV, what I can do is I can just sort of brute force say this is equal to sigma P times phi of pi kV. So this, by brute force, it works out. And there are things to check to make sure this works, but this is OK. So you have to check that this is a GK. So it has to be checked. And that's not a trivial exercise. Hang on for 1 minute. Let me just finish writing. Of course, it's a K-map. That's pretty easy, but it's a Lie algebra map. It's not quite so right. Molly, was it you? Oh, yeah. P is in capital P, no? Oh, I'm sorry. PK, right. Right, very sorry. Okay. So already, just so we fudged this because it sort of seems kind of stupid, but there are other ways. So there are other ways to deal with this. In fact, this problem gets worse for other groups. So let me just make a remark about that. So this is not quite it's not deep, but it's not quite trivial. You really have to sort of think a little bit about how you go about it, but it's possible. So that's all right. So this problem gets worse for other groups. For other real groups. So in that case, if you can have a parabolic P which is large. So I'm just mentioning this because in the literature that it's dealt with in, I would say, a somewhat confusing way. And sigma U can be infinite dimensional. Well, SLN, SL3, how about SL3? Next time we give this course, we're going to talk about SL3. We figure we can keep getting grants forever if we sort of just keep going. I'll leave it in my will that, I'll bequeath the lectures to somebody else. We're going up to 3 for the next time for sure. So, reductive groups actually. Algebraic reductive groups, although even that's a bit restrictive. Okay. But the point is that if I'm looking at, and in this case, so for example, we can have SL3. And if I take SL3, then my P is a parabolic. I can take like this, and then the reductive part is equal to GL2. So P, in this case, is equal to GL2 cross, well, just GL2, in fact, because the determinant, this has to be the determinant of this for SL3. And so I'm inducing, so sigma can be an admissible representation. So it's no longer, I can't even assume it's a representation of P. So it becomes, all these technical conditions become, so I'll just put a single word on the board to denote what happened. I'm not going to tell you exactly what the solution to the problem is, but it becomes messy. There's no question about it. So the key to keep in mind, I think what happens is, we've told you the solution to all these problems. The secret is you don't need a representation of the group, you just need the matrix coefficients. So the trick to handle all these problems, well, there are two tricks to handle all these problems, which we've told you about. These technical problems. Maybe I said right in my maybe my second lecture that the whole problem of representations of these groups is that you don't work with representations of the groups. And the first is, we do know the existence of matrix coefficients. Even though the group, we don't have an action of the group, we do have matrix coefficients. That we do know that the GK modules have matrix coefficients. And there's something we haven't explained to you, but which follows from that. We do have an action, not of the group, but we have an action of the part of the group algebra by K finite functions of compact support in G. So we don't get an action, I don't get an action of the full CSE infinity because it's not a representation of the group, but knowing the existence of matrix coefficients, you can deduce that the by K finite stuff acts. Yeah?
Is it obvious that here FV is K finite? I mean, the image of FV is...
It's obvious, yeah, it's obvious that it's K finite, I think, from, okay, but yeah, no, that's, I mean, no, there are definitely things to check. I mean, they're not. So whatever, I'm shoveling it all under the rug, but it's not terribly hard. I think it's more important that I give you some perspective on this rather than that I go into the details. There are definitely things to check, but you have to, it is. So I mean, there's another solution, which is you can find some representation of G in which V embeds,
Right.
and then show that it's independent. So let me just make a remark. So another way to deal with this. So we embed V included in something, and then show independent of the embedding. So this is a G space. So there are several different strategies. Nonetheless, all these problems, this is a sort of, when you're dealing with representations of these groups, continually you're having to deal with the fact you don't actually have a representation of the group. Yeah.
Is this algebra of Bic infinite functions, is it independent of the actual G? Whatever G you take, actually whatever group you...
Whatever K you take.
No, Bic finite, given the Lie algebra, given the Lie algebra in K,
Yeah.
does it, is this algebra of Bic finite functions on capital G actually independent of capital G?
No, it depends on capital G, but G and K determine, GK determine G. The point is that GK determine G. If I tell you the Lie algebra, then I'm telling you the simply connected covering of the connected component of G, and if I tell you K, then I'm picking out which quotient and what the number of connected components is. So this is the same data. We should have stated that. Actually, I don't think anybody in the literature states that, but it's certainly right. We should have stated that more explicitly too, I think. In fact, we should have made that a theorem. Right. When we do SL3, we'll do it right. Okay. Yeah. I'm sorry, you have to yell really loud. My ears are not so good.
We don't have a P action on that U.
Yeah, that's I mean, that's right. I mean, I said we had problems here, but at least here, that P is equivalent because it's a finite dimensional representation. These are the same, but over here, I don't have an action of P, so you have to really work hard. It's no question about it. You have to work hard. There are, again, several different solutions. The first and simplest solution is just to embed this in a representation of P and then show it's independent of that. But you're right, there are problems right from the beginning. Problems right from the beginning. I can't define the induced space directly because I don't have a representation of P. Exactly right. But over here I do because representations of P and K, this is finite dimensional representation, absolutely equivalent. There's no problems with extension. Wait. No, the fact that you don't have, so now let me tell you what the best solution is, but it's very, very hard to verify. So the best solution to all these problems is to construct canonical representations of G. So it's not easy to verify, but so there's another kind of solution to all these problems. So one way of solving these problems So one way, as I said, of solving these problems is to use the fact you have matrix coefficients and somehow work technically with that, sort of reducing constantly questions about the group to questions about the matrix coefficients. But one way of solving these problems is to find some really good ways to extend the representation from GK to K to G. And then show it's canonical and exact and faithful and all very nice properties. And that's been done. I don't think there's no really simple way of seeing that, although there is in principle a way of doing this. Somehow it's never actually been worked out. And so there are two ways to do this which have been done. So this has been done in two ways. And they're both illustrated over here. So one way is, and they both start off with the same fact, I embed, or they can be done in the same way, I embed my V in a principal series in some I sigma. U equals finite dimensional representation of P. Okay? So I know I can do that, and being able to do that, as Dragan explained.
This is only for SL2R. This is only for SL2R?
No, it works for all groups. Okay. I can always embed. What Dragan explained was that if you use matrix coefficients and you use the differential equations that are satisfied by matrix coefficients, and you look at the asymptotic behavior of the matrix coefficients, it gives you an embedding into some induced representation. And there's another proof of that which uses D modules, which I don't think he's mentioned, which he may mention today or tomorrow. Anyway, so this is possible. There are two different proofs of this, quite different proofs. Yeah, this is the principal series. This is the induced representation from P. This is ind U P. It's a GK module. Yep. Yeah, it's a GK module. So that's one way to proceed. And there are two different proofs that this is possible. So it's a good result. One uses matrix coefficients. One uses some fancy D module stuff. Any other? There's a question here somewhere.
Is P any parabolic?
Yeah, P is the minimal. P is a minimal parabolic. Okay. So that's always possible. Both proofs become somewhat complicated in higher rank. But they both work. Both proofs work for arbitrary groups. Okay, so I embed V in something, and then I define, well, V omega equals the closure in ind omega. In other words, I embed my GK module into this GK module of K finite induced representations. And then I just take the closure in the analytic functions, or I can define this equals the closure in the smooth functions. And after a tremendous amount of work, it turns out that both of these are totally independent of which embedding you choose, and that these are both exact and functorial. So both these constructions are completely canonical. They're different from, they're definitely different, but they're canonical within themselves. Okay. So as I said, V omega is the smallest, in some sense the smallest one. You have to prove that along the line too, or it falls out from what you do. And so that's easy. It's somewhat easier to work with in some ways than the other one. This one is the smallest one with some other properties I haven't mentioned. But both of these are completely canonical constructions and give you very nice, so you have two different ways. You have basically two really nice ways of extending a given GK module to G. The price you pay for this, well, the proofs, there's not too high a price to be paid. The one price is that the proofs of both these constructions are really nasty. I don't know of any really pleasant constructions. Proofs are yucky. I'll just make. I'm not sure I've ever written the word yucky before in the blackboard. Yes?
The Hilbert space is not canonical though. The Hilbert space.
No, absolutely not. The Hilbert space is not canonical at all. So, I mean, I could take L, and furthermore, what is true is the following though. So if I take my I, so I could have continued, I could have said I2, right? This would be L2 functions on K. That's sort of, well, that's kind of non-canonical. But what's true is that this is the smooth functions in this, and this is the analytic functions in this. And so that's right, it doesn't matter. In fact, yeah, okay. I could have embedded an LP. Again, I get the same thing. So these really are canonical in some sense. These are the analytic vectors and representation. These are the smooth ones in some large class.
But if you have these two ways to extend it, you have two more equally natural ways to
The duals. Yeah. They're not so nice. But yeah, sometimes you have to work with those too. And so if you work with the duals of these, then it's very interesting. This leads to the theory of hyperfunctions, to which I repeated before. And this leads to the theory of distributions, which is maybe not quite so bad, a little more intuitive perhaps. But anyway, yeah, so again, there's some, so these are proper analytical objects in some sense. Okay. Okay, so that's one way of dealing with it. I say that leads, the proofs of these constructions, that these constructions are nice, are all yucky. There's, yeah, no, and everything's independent. I mean, that's part of the theorem, is that it doesn't depend on which sigma. You could choose lots of sigma. There are lots of sigma which you could choose, but it really doesn't matter at all. So it's a very, in some sense, it's a very nice theorem. So that's one way of dealing with these questions. And in the long run, my guess is that that's what people will do. Like 20 years from now, I think people will design the whole theory differently, starting with these constructions. And my personal favorite is this one, and Heck's personal favorite is probably the other one.
Well, depending for what?
Yeah, depending for what. So that's right. So my personal favorite, that's because I invented it. So we should call this M for mine, but we'll just call it so. But there are reasons. There are reasons for it. It's not just a question of egotism. That's my favorite. I like to work with distributions, and I find hyperfunctions totally repellent. But there are other reasons to work with that other than aesthetic qualities. Anyway, but we don't need to, and we're avoiding having to deal with this question because, as I say, the proofs are so yucky.
So how does this relate to this problem of?
Well, then, in this category, you can just define the same proof that I gave for finite groups works. Once you know all these things, then the proof just works without any modification. So that's a beautiful fact. Right. Okay. Okay, let's go back again. So, as I say, this is variations on Frobenius reciprocity. Now, I want to explore this a bit more. So now let's assume we know. So we know that Ham GK, whatever proof we use, let's assume we know that this works. And let's write it like this. Okay. So this is the version we'll use. And then I'm also going to use a slightly different version. I'm going to state it this way. I'm a little bit fuzzier here. Ham G from V infinity into end infinity. I'm not going to say exactly what I mean by this, but this is a smooth representation of the group, and this is P from V infinity into U, and this means continuous. So there's some version for the Lie algebra and there's some version for the group. And I'm not stating exactly what I mean by this because this is really the version I want to use, but we'll see I'm going to do something with the group itself. So this is a philosophical version, so to speak, of the principle.
So here you need the largest possible globalization.
I don't need anything. And it works for almost any smooth. As I say, it's a philosophical thing. I just want to say there's some category in which this makes sense. I don't. I'll show you what I mean. I'll explain what I mean in just a moment.
Don't you need duals on the right side? You need to take U dual inside
No.
infinity dual.
No. There is some relation with duals I'll explain in just a minute. Okay, now, so I've talked about arbitrary finite dimensional representations U. So there's a fact you have to know about finite dimensional representations of P, which I haven't said. So far in this course, we've worked exclusively, I think we mumbled now and then. I think we've worked exclusively with a case where it's an irreducible representation of P. So if sigma U is irreducible, then Nx trivially. N is contained in the kernel, and therefore the Lie algebra N annihilates U. And that's because the subspace the subspace in which Nx trivially is a proper subspace, if the representation is irreducible, then it has to be a proper subspace, and but it's reducible, so it doesn't work. So this is a work size. But second of all, in general, the image of N in the automorphism group C of JLU is unipotent. Or equivalently, U is annihilated by some power of N. Okay, so that's actually easy. I'll just leave that as an exercise. That's easy to show, and it will appear in the notes when we put all this stuff up. So, yeah.
Why in general? So what's the case for that?
Because it's finite dimensional. So there's some fact from algebraic groups that says if I...
Yeah, sorry, in general, but that means that there's some exceptions.
No, I mean always. More generally, yes. More generally, yeah, always. For an arbitrary U.
So you're not talking about like a generic.
No. For an arbitrary finite dimensional U representation of P. See, this is not true if I just have a representation of N all by itself, because I can, I could have it, N, for example, N is just R, so there are lots of representations of R which aren't unipotent. But if I throw in the fact that P acts, then I have this A acting. So the basic idea is this. I take U and I represent it as a direct sum of eigenspaces under A. And I know that my N shifts these around. And so if it were not unipotent, then I'd have an infinite number of these things, so only finite numbers. So N shifts these. So only a finite number. This is an argument which Peter basically made the first day. Okay, so that's the way the argument goes. So I have to have the P action as well as the A action. Okay, so this is, so now I can rephrase, given this fact, I can rephrase this version. I divide by some power of K. So the slightly different form of Frobenius reciprocity is that if nk of U equals 0, So hum of pk intersect p of v u is equal to hum pk intersect p of v modulo nkv u if nku is equal to 0. So that's just a formal step given by the fact that I know nk ex nilpotent. So if I think of this dually, now I'm thinking in terms of duals. I look at this, I take everything, I just take continuous, well, I take just linear duals here. So it's equal to hum pk intersect p of u hat into v hat. And if I translate it over here, it's hum pk intersect p from u hat into the v hat torsion, which I write like this. And v hat, so let me explain. V hat n equals the union of subspaces of v hat annihilated by some power of nk. Okay, so this is just, so I'm just making formal shifts. There's no topology here, this is just a linear dual. This is not so exciting, but it'll give you some feel for what I'm about to do next. Any questions? So I've taken a sort of I just have made a series of abstract steps. Okay, so this is another way of, so now let's look at one particular representation. So let's look at the irreducible principal series for SL2. I should say, this is the first of 2 lectures by me this morning because Dragan had to stay home and have his window fixed. His window was broken by the wind last week. So you're going to get 2 doses of me. So take V equals in U. Okay. And U irreducible. And so now I've defined, very briefly, and I'm going to take it to be, actually, I'm going to take it to be this, and we'll see why. There's some technical thing. I'm just taking it to be the smooth principal series, and this is necessary for reasons you'll see in a minute. So let's see, these are smooth principal series, and now let's look at one example. So I'm going to define something called the Bruja filtration of this. And this is where you have to have C infinity functions, where the analytic ones won't work. So I let IW, so this is my V. Well, I'm going to call this I infinity. Now I have something called I infinity W is included in I infinity. And what it is, it's smooth functions which vanish of infinite order along P. So let me remind you, I have the Bruja decomposition. G is equal to the union of PWN and P. This is basically the union of projector space into an affine part and infinity. And I take, so P is a subspace of codimension 2 here, and I just take my functions which vanish at infinite like that. So for example, if I'm looking at C, if V is equal to C infinity, well, if V infinity is C infinity of P1, then it's very easy. Here's my functions. And as I think I drew this picture before, I take those things which vanish of infinite order here. So the Taylor series at infinity is equal to 0. Okay? Now, I can't do this. Why do I have to use smooth functions here?
I mean, as opposed to analytic? As opposed to analytic?
Yeah, as opposed to analytic. Yeah, so I have to use the smooth function here because if I have an analytic function which vanishes in for it, then it vanishes, period. The Taylor series determines the function. So even for K finites, there's no such filtration. But for C infinity, there is such a filtration. It turns out to be extremely useful when discussing what this space looks like. And now, there's a theorem which is extremely important, which I'll remind you. Some of you may have seen it, but probably not. I have a feeling that in analysis courses, they don't teach you real analysis. They teach you some abstract nonsense, but that's my own conservative bias. So let me tell you a theorem of Emile Borel. So let U equal an open neighborhood of 0 in R. Okay, so here's R, here's U, here's 0. If I take a function, just in C infinity of U, the value is in C, it maps onto its Taylor series. At 0. And that's a member of what's called the formal power series of X. So it's an infinite series. It looks like this. Okay. Does anybody know what Borel's theorem tells me?
We know that it's surjective.
It's surjective. That's Borel's theorem. Not trivial. It's not a terribly difficult theorem. On the grade of difficulty from 0 to 10, it's about 5. So the map, it's an interesting theorem, actually. I'd say it's not trivial in the sense in which all proofs are interesting. So the map from C infinity of U to formal power series is surjective. Okay. So if you give me any formal power series at the origin, somewhere in this universe exists a smooth function which has that Taylor, and defined in a neighborhood of 0, which has that Taylor series, which has that as its Taylor series. There's some interesting aspects of this. This theorem plays an important role in analysis on manifolds, and it's a tricky theorem because there's no splitting. So what we have is we have a map from C infinity of U goes to Cx goes to 0, and what you might call C0 of U is the kernel of this. So these are the functions which vanish of infinite order at the origin. So we have what this theorem gives you is an exact sequence that looks like this, and the sequence doesn't split. There's no sort of lifting of this space into this. It's a very beautiful fact. Again, a non-trivial theorem. This is used a great deal by topologists when studying maps between manifolds.
Easy part of the theorem? I think it's splitting is the easy part of the theorem. Because if it's split, then you'd have something given by a Taylor series that doesn't converge.
Let's see, is there an easy proof?
Well, so I mean, if there was an Erbium function that was given by its Taylor series, right? That would diverge.
So let's see, so I'd have,
You have a function that actually is given by its Taylor series, right?
no. So this is an interesting point. I'm never quite sure what to, I love calculus, actually. If I could teach calculus to honors math majors, instead I teach them to those damned engineers. But the truth is that Taylor series give an asymptotic expansion, not a convergent expansion. It's a rather subtle distinction, but again, the more analysis you do, the more interesting that becomes. So just because it's split wouldn't mean that I would have an analytic function, which is, Taylor series are asymptotic. We can talk about that some other time if you want. It's something I always debate whether to introduce to graduate students because it's not used, but it's an asymptotic expansion, not a convergent expansion. This doesn't say anything about converging series. Okay. And that's what makes the theorem, there's no obvious, as far as I can see, I mean, I could be wrong, there's no obvious reason why this doesn't split somehow, at least as far as I'm concerned. I don't see any immediate reason. I don't think it's a triviality. It may be, maybe I'm just missing something. At any rate, the consequence of this is that, so let's see. So I have my function v infinity. I'm almost through. I'll stop and continue. So we have iw infinity goes to I infinity, goes to something I'll put in here in just a moment. Actually, it's going to take a bit of space. So let's see. So iw infinity are those functions in the C infinity principal series which vanish of infinite order along P. Now, if I'm looking at actual functions on the projective line, I can look at Taylor series. But in general, I have to be more tricky because what I have is, now to sort of think, I'll just give you a sort of an intuitive picture. I have this P sitting here, and my condition on functions in the induced representation are that they behave in some nice way along P. And so I can't just take Taylor series anymore because I have to somehow include that covariance along P. And the answer to that is the following. It's a formal power series. So the space I look at here is Hom UP. Actually, it's UP and K, in fact, is what it is, from UG to U. Goes to 0. So this is what, and basically this is a Taylor series. I have a function, a member of I infinity, goes to the map, X goes to XF, evaluated at 1. So let's see, let's go through that again. If I have a function in I infinity, I can evaluate it at 1, but I can also first apply the derivative. This is Rx. This is the Lie algebra acting on the right. I can also first apply a derivative, a second order, a higher order differential operator, and then evaluate that at 1. That gives me a map from this to U, because this takes values in U. So this gives a map from this to this, and if you check the conditions on the induced representation, it means it's a P map, basically. So this is a kind of Taylor series. It's what replaces the Taylor series in when I'm inducing representations. And then it turns out that there's some easy way to just reduce the statement to Emil Borel's theorem. You look locally and somehow fiddle around, and that's what you get. So this is what I call the Bruhat filtration, or the Bruhat exact sequence of the induced representation. Okay, so in the next lecture, I'll start with this and explain what good it is. Okay. Question, Jones? Yeah.
Here you said, so you take functions with vanish to infinite order.
Yep.
To infinity.
Yep.
So obviously, so you can't take analytic. So the work if you take analytic.
You're right.
But what if you just require that they vanish? Period. No.
A finite order, you mean?
Yeah.
Yeah, you can, yeah, well, so then you have a whole bunch of filtrations instead of just one. So for technical reasons, it's much nicer. I'll explain. I think when I explain, so I'm going to, when I start the next lecture, I'm going to start off by describing more about what this term looks like. And when I do that, I think you realize that the technical gains you get by this are enormous. That this is a very nice space, in fact. It looks like a horrible space. In fact, it's a very nice space, and I'll explain why. So I think when you see that, it's true you could somehow look at analytic functions or even K-finite functions vanishing of some order and take the direct limit, but it's much nicer to do this. Yep.
Do you need an enveloping algebra syntax statement, or you could just use P and G?
No, I need the enveloping algebra because it's only a P. No, I need the enveloping algebra. This is really a Taylor series, so if it's something purely algebraic. It's not a, so what, well, I'll explain. I promise you I'll explain more about this exact sequence in the next lecture. There's reasons why this is there. Okay. Okay.
Do we get a simpler statement for SL2R?
No. No. Okay, I'm through. Don't clap yet.